Back in 1820, when Joseph Fourier first guessed that the Earth's atmosphere had a warming effect on the global climate, the science didn't yet exist to explain the greenhouse effect. He just guessed that the atmosphere acted like a blanket, capturing solar energy and raising the surface temperature of the planet. Since then, scientists, with the help of balloons and satellites, have been able to measure the amount of solar energy absorbed by the atmosphere as well as the amount of energy reflected back into space. According to the World Meteorological Organization, 70% of incoming solar radiation is absorbed by the atmosphere and the Earth's surface, while around 30% is reflected back to space and does not heat the planet. Scientists call the inbound solar radiation irradiance. Not a great word, and one that causes a lot of confusion. Sunshine would have worked just fine. Scientists call the thermal energy or heat given off by the surface of the planet and its clouds radiance. As you may recall from your high school physics class, energy behaves as both a wave and a particle. Irradiance is concentrated in the visible light spectrum. Visible light hits the Earth at relatively high frequencies, and the wavelengths of visible light are pretty short, at 380 nanometers to 700 nanometers. NASA compares the wavelength of blue light to the thickness of a soap bubble membrane. In this graph, the wavelengths of irradiance are shown on the horizontal axis, and the intensity of irradiance is shown on the vertical axis. Adding radiance, outbound radiation, onto the same graph, side by side, shows that radiance occurs at much longer wavelengths, deep into the infrared or heat spectrum. Radiance occurs at wavelengths between 4,000 nanometers and 50,000 nanometers, with the highest intensity around 16,000 nanometers. Note that the inbound irradiance and the outbound radiance being reflected back into space don't overlap. As we all learn in school, the Earth's atmosphere is composed of 78% nitrogen, 21% oxygen, 0.9% of argon, and 0.1% other gases, including carbon dioxide, methane, nitrous oxide, and ozone. It turns out that this 0.1% plays an oversized role in climate and the greenhouse effect. These ratios refer to dry gas, air without water vapor. Water vapor can range from 0.2% to 4% in the atmosphere, depending on local conditions. As we will see from the data, water vapor is the most important greenhouse gas, even more important than carbon dioxide. Humidity absorbs both irradiance coming directly from the sun and radiance as it's reflected back into space from the surface of the Earth. That is why a humid 60-degree day can feel hot, while a dry 60-degree day can feel cool. This section of the chart adds on to the graph the energy absorption of water vapor at specific wavelengths of irradiance and radiance. The black areas show the proportion of energy absorbed or scattered at various frequencies. If the black area fills the entire section of the graph, then 100% of the outbound energy is being absorbed and can't make it through the atmosphere to outer space. Concentrate your attention on the radiance or infrared sections of the chart. These deal with heat. Note how water vapor absorbs some incoming and most of the outgoing radiation. Again, absorption is denoted by the black areas. The white areas are windows in the spectrum where energy can radiate back into space. Now let's layer CO2 absorption onto the graph. Note that CO2 absorbs outbound energy or radiance in a relatively narrow range of spectra, around 16,000 nanometers. Also note that CO2 blocks escaping energy in a wavelength window where water vapor lets 60% of the radiant energy escape. As it turns out, this energy window is really important and represents about 20% of all thermal energy that can be potentially reflected back into space. The more CO2 blocks the 16,000 nanometer window, the greater the greenhouse effect, and the higher the average temperature of the planet. That is why CO2 matters so much. Methane and other greenhouse gases also block radiance at other important frequencies, but they work a bit differently from CO2 and will be covered in a later video. Currently, the CO2 concentration in the atmosphere is around 410 parts per million, or 4 CO2 molecules per 10,000 air molecules. That sounds very low at first glance, but that level is up from 275 parts per million at the beginning of the Industrial Revolution. If the concentration of CO2 in the atmosphere keeps rising, the amount of radiance escaping into space will decrease, causing the average temperature of the Earth to rise, and that will have dire consequences on sea levels, ocean acidity, biodiversity, weather, and food production. To meet the COP26 Climate Pact's goal of a global average temperature raise of no more than 1.5 degrees Celsius, which would raise the global average temperature from 14 degrees Celsius to 15.5 degrees Celsius, the increase in atmospheric CO2 and other greenhouse gases must stop and then decline. One of the problems with CO2 is that according to NASA, it can remain in the atmosphere for a long time, for between 300 and 1,000 years. Yes, you could be breathing in CO2 today that was created by the fires lit during the sack of Jerusalem in 1099 at the time of the First Crusade. And yes, eventually nature will recycle all the excess carbon produced by fossil fuels and sequester it back in the soil, rocks, and oceans. But by then, the environment and the weather will have changed, and mostly for the worse. So we can't rely on nature to solve this problem for us. Mankind needs to step up to the task, take responsibility for the CO2 it's generating, and accelerate the CO2 removal process.